Top of the hour. Lab today and tomorrow, recrystallization, and there's video for that, yeah. And then I think Wednesday, Thursday, we're doing a bromination of an alkene. Reacting using bromine. Okay? Other questions before we get going? We'll do this mechanism here. Any other questions? Anything about lab? Any questions about lab? Lab reports will be returned in lab. You also will be turning in your SciFinder literature assignment when you come to lab. Okay, mechanism here. Looks like a 7-member ring going to a 6. Looks like we got an alcohol. It's a hydration reaction. Alkene to an alcohol. Maybe you want to take time to do formula. If you do formula, you'll see that this formula has H2O added. But, you really don't need to do all that. Kind of see, we're going to get a 6-member ring from a 7. A lot of these reactions are sort of just consistent. Ring expansions, contractions, alcohols, hydride shifts. It's a lot of the same things. Okay. First reaction is just alkene. I mean, what reaction do you know? The only reaction you know is an alkene reacting with what?
Hydrogen.
Well, H plus here. We know some other reactions now, but you got alkene and H plus. Because alkenes don't react with pure water. This is H plus in water, correct? So this is the only reaction you have. Where are you going to make cation, top or bottom?
Top.
Either way it would be secondary. But, and that could be one of the toughest decisions, and you could get there. Lots of substitution on this carbon. If we're going to make a carbocation, we might like to eventually get it here. Very substituted carbon. So for that reason, and perhaps that reason only, I'm going to put the cation at the top. That means I'm going to react these electrons down, and that's going to give UH here, cation here, 2 methyls there, yeah? What cation do I need? Sometimes you can back up, not always, but I need, if we had that cation, could you get home from there? Yes. There's a carbon with 2 methyls. Do we have a carbon with 2 methyls right here? Anybody get the cation there? Yes, if these electrons here break away from this carbon and go bond over there, and it looks like a long way there, but this ring is really a little bit different from how I draw it. These electrons here, pull them down away from this carbon and connect them over here. All right, somebody pull that pin down. That's your arrow movement. Pull it down, and yes, it's going to bond over here. It looks like a long way again. Just boom. That's it. What does that give? I'll try to draw it just like this. Boom, 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 boom. And this is boom, boom, boom. That used to be here. We pulled it down and made it go bond here. Yes. See what we did? What's here now in this carbon? It's missing a bond, so now it's a positive. How many H's on this carbon?
1.
1. 1 there, 1 there, 1 here. But there's 4 bonds there now. That's now neutral. Here you go. These electrons moving away. It's like this carbon here, instead of bonding here, it bonds over there. That's an alkyl shift. But it went from a 7, now the ring is what?
6.
Now it's a 6-membered ring, and what is that? Well, that's that. It's a 6-membered ring, coming off of it a carbocation with 2 methyls. Carbocation with 2 methyls. Now what attacks the cation? Water. Bam. Those electrons add there. Oxygen now bonded. We've not lost any H's yet. That gives that. How do we get home? Something takes the H. This is very generic. No minus is even shown here. Some minus could take the H, or we could just have water take the H. These electrons take the H. These electrons stay behind. We form that plus what? Yes. The acid's reformed because this is water and acid. Right here, water reacted, but the acid was there at the beginning, and now it's reformed. The acid is sitting with another molecule of water. Question?
So if we're just given like the front half of that reaction, is it always gonna expand or contract?
You mean,
Like
okay, there's 2 different types of questions. Mechanism questions. You're given the starting, you're given the product, provided mechanism using appropriate arrows. Is a mechanism question. You're saying if this was a predict the product,
Yes.
that is, show the product.
Okay, so,
This would be more difficult.
yeah.
Now I could say show the ring contracted product, but it could have, this could have rearranged another way. What if a methyl shifted? I mean, you could do a methyl shift and put a methyl here, cation here, still 7-membered ring. That's reasonable. It still went to a tertiary cation. Yeah, that'd be a little more difficult to predict the product. What size rings are best? 5 and 6. So it did go to a better size ring. Yeah? Okay, good. Let's see how to do on the THC. Pretty straightforward. Everybody see it? Anybody confident you got the mechanism here? Yeah? How's it look? Looks pretty good. I would, the first arrow, maybe a little bit more precision. You know where the new H is, right? I usually draw in the new H that we just added. Good? Making this bond right here, making this ring, alkene, H plus catalyst, yeah? This alkene attacks the H plus. Where do you leave cation, top or bottom? Top. So we pull away from that, and we end up with boom, 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 boom. New H here, cation here. I'm just going to cut this off, or I'm just going to make it like this. That leads to this, and right next door you have a nucleophile. And these electrons can then bond here. That's going to make a 1, 2, 3, well, you can't see here, but 1, 2, 3, 4, 5, 6-membered ring. So you have an internal nucleophile. And so you're going to get the oxygen, we just made that bond. This carbon has two methyls. That's a methyl and a methyl. There's still an H there, and that's a positive charge. Okay, the rest is up here. And then something takes the H. Well, there's got to be a minus here. There's also probably water here. You do water your THC plants, right? Or it rains. Got to have water for a variety of reasons for your plants. Take the H, these electrons stay behind, and there you go. You just made that by an intramolecular reaction. Alkene, carbocation, nucleophile. Pretty straightforward? Yeah?
And both of those are actually formed, right?
Both of these intermediates? Yes. Okay, so this should be pretty darn straightforward right here. You should assess your progress. If you're having totally difficulty with this, something's not going on right. You're not making enough progress, you're not using your textbook enough. Alkene reactions. There is another alkene up here, but clearly it's not done anything. It has not reacted. Could it have? Certainly. Maybe there's another product that's made by the THC or the plant that involves reacting up there. But in going from here to here, that upper alkene is not reacting. Is there a question? Yes.
When we do our mechanisms, are we required to circle the lone pair, or can we just have the arrow going, leading from the lone pair?
Not required to circle the lone pair. I highly recommend it. Highly recommend it because I think it will ensure that you are doing your mechanisms correctly. Because every arrow you move begins with what in your mind? These electrons attack here, these electrons do this, these electrons move here, every arrow begins with these electrons. If you're not doing that, then you're probably, there's potential that maybe you're not moving arrows right. Okay, let's see where we're at. Pink sheet is our outline, right? B, electrophilic additions without a carbocation. Mainly because we got back bonding. Cyclopropanes we finished up with. Back over here on our outline. Right here. We're ready to look at the last two reactions up in here. They're both ways to make alcohols. Alternative ways to make alcohols. Alternative ways to hydrate alkenes. But we're not just going to be using aqueous acid. That's sort of the introductory, the first way we saw. H3O+. This is two new ways. We'll talk about the usefulness of each way. But first, Roman numeral 5, oxymercuration, or alkoxymercuration. Adding water or alcohol to alkenes without rearrangement. By the way, none of the reactions under B will have rearrangements. Why? Because there's no carbocation. You only get rearrangements when you have a carbocation. since B reactions do not have one, you don't have to worry about rearrangements. And that's the one good thing about this method for hydrating. You don't have to worry about rearrangements. Okay, over in the handout. Top reaction here, if you hydrate this alkene with aqueous acid, the major product is actually this. I think we showed this. And to get here, what had to happen? The carbon cation rearrangement, particularly a hydride shift. Let's see, there's an H here. The H is gone. The new H is actually over here. Okay? Carbocation rearrangement by hydride shift. You should be able to see that. But what if you wanted this product? That is the old, well, cation, and water adds here where cations should be originally. You can get that using these reagents. It's a two-step process, okay? Remember the 1 and 2? They're not combined. That's 1 week. Done. There's going to be something made first. Then we come back and we react that thing with this other reagent. Okay? So, first reaction, mercury acetate and water. Mechanism. Well, your mercury acetate, everybody should know acetate, right? Right? Acetate. Yeah? Anion of acetic acid, yeah? What's the charge of the mercury here? Plus what? 1. I can't hear it. It sounded like you said 1. 1? But you got 2 acetates. So the mercury should be plus 2, right? Okay, that should be pretty easy. I mean, what's the charge of the magnesium here? I'm having trouble hearing. Sorry, guys.
2 plus.
2 plus. Okay? Yes. This is ionic, right? You know ionics? Okay. We can show this, maybe one of the acetates disassociating. And we can get to mercury acetate. We just had 1 there. What's the charge of the mercury? Yes. Okay, if we lose 1 acetate. If we lose both acetates, the mercury is then 2 plus. Right? Okay, mercury plus, a lot like an H plus. Right? The alkene can attack the mercury plus and make a bond to the mercury. Where are we going to leave cation up here, top or bottom? On the bottom. Okay, this is now bonded to mercury. And we can show the acetate still there. What do we have here? Cation, right? Okay. Is this cation actually formed? Cation actually formed? Or not? Why not? Showing. I thought you were going to say because we were under letter B, and letter B says reactions without carbocations. Do what?
So we're not under D.
We're not under B?
We are,
Yeah.
number 5. We are.
We're on B5.
Is it because of the backbone?
So that's why, right? Because we're under B. No carbocation, right? According to the outline, no carbocation. All right. Why no carbocation?
No back bonding.
Back bonding by what? No, not the oxygen lone pair. Mercury has lone pairs, at least one. I don't know exactly how many, we'd have to think about it. Mercury has at least one lone pair. The mercury back bonds. And what does that lead to? Mercury is now bonded. You have this three-membered ring, like a bromonium ion, etc. What's the charge of the mercury now? Charge of the mercury? What was the charge of the mercury here?
The Alkene attacked
It's plus here,
But then it bonded, so now it's just.
but then it bonded, so now it owns one more electron, so because it owns one of the bond. So if it's plus and it gains an electron, it should be neutral here.
Yeah.
But now it doesn't own the lone pair entirely. It only owns one because it only owns one of the bond. So it should be what over there? It lost an electron in terms of its ownership count. So this should be what? Yes. And that's called a mercuronium ion, like a bromonium ion. So what do you think about this? Actually part of the mechanism, or is this just us on the board?
On the board.
Just us on the board. This is NAF. Same old thing. As soon as the alkene attacks the mercury, what is the mercury lone pair doing?
Back bond.
And that's happening at the same exact time. There's only one transition state. Bam! Here's your first intermediate, mercuronium ion. Same discussion as before. No cation. Water. Water attacks. Where are we going to attack? Right or left? Same question. And actually the answer sits right here, the same place there would have been a cation. Why do we attack here? Because this mercury pulls. It may not pull as much as the bromine, but it does pull some because it's positive. It wants electrons. These electrons are attracted this way. More positive is going to develop here than here. Why? Because this carbon has a rich friend. So it allows more positive to develop there. Okay? More positive here. Not a cation, but a partial positive. These electrons attack here and kick these electrons back off onto the mercury. Thanks, mercury. Thanks for stabilizing this cation. Well, it actually never formed. Thanks for stabilizing this intermediate. Water comes in. We'll give you your lone pair back now. What does that give? I'm going to raise this up. Well, actually, I don't need to raise that up. I just need to move over here. I'll write over here the outcome of this. What do we have? Boom, 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 boom. Mercury acetate. What's back on the mercury now? Lone pair got back there. That's what the arrow means. What's on this carbon here? Water has added. You have not lost an H. That's a positive charge. Okay, now we lose an H. What can take the H? There was a minus here that I erased. Yes, remember there was an acetate that ionized? It can take the H, these electrons stay here, and we get boom, 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 boom. Now I have an OH here, plus what? plus acetic acid. Right here, we make acetic acid. You should know the structure of that right there. Right? Acetic acid. An acyl group. This is an acyl, right? You learn in Gen Chem. Acyl is abbreviated AC. ACOH. ACOH. Just written a little bit backwards, but it's, all right? Acetic acid, right? Here we go. This is in step 1. That's what you have after step 1. What have we done to the alkene? What type of product did we make here? We added an oxygen, and we also added what? Across the double bond. Used to be a double bond here, we added two things, so the term across the double bond. Oxygen on one end, mercury. Oxymercuration of the alkene. Oxymercuration of the alkene. That's what step 1 is. In this reaction, we could have also used an alcohol here. If we had used an alcohol, this would have been an OR group. And we could call it an alkoxymercuration if there was an alkyl group here. What do we need to do to get from this to the end product? What do we need to do? Yes, but what needs to happen to get to the end product? Got to get rid of the mercury and the acetate. What needs to replace the mercury here? Yes, there's 2 H's here. How many H's on the end product? We need to replace this with an H. We actually need H minus here. This is H minus source. Sodium borohydride is an H minus source. So boron with 4 H's. And what's the charge of the boron? Minus. And we got to have a cation sitting with it. And we can have such. It's called sodium borohydride. Very common. It's an H minus source. Boron is hard to make boron happy. It either doesn't have an octet. Well, here it's got an octet, but that leads to it having a negative charge. Boron is like, you know what? I don't like being negative. H, you and your electrons, get out of here. And it shoots that off like darts. Because if that leaves, what does the boron become? Get rid of that. It just becomes this. I'm saying these 2 electrons go with the H. No electrons. It's now neutral. A neutral boron. Okay? If it loses an H minus, put a charge there, that's loss of H minus. Okay? So these things are like shooting these darts off. All right, now this may not be the correct mechanism, but I'm going to do it this way anyway. The H minus, again, I could bring in that entire reagent and show it coming from there. We can also just do this. Okay. Where does it come from? Over there. We just explained how. These electrons come in here and attack this carbon. And kick these off, like a leaving group. What does that give?
The product.
I guess final product. You're going to have an H there in place of... That's it. Final product.
When we do this, you had just stuck like one lone pair on Mercury just to show that that's the one we're working with. On a test, but we need to show all the lone pairs.
One is enough.
Okay.
For Mercury. Other things, simpler things, you should show all lone pairs. What's the fate of the Mercury here? It gives final product. Okay, this goes to product. What's the fate of the Mercury? What does it become here? Mercury acetate. I'm showing, okay, one lone pair. What is this? Another lone pair. What's the charge of the Mercury now? If it's neutral here, and this is becoming a lone pair, what should be the charge here? Negative. Now, if we lose the acetate, we make mercury plus acetate, and acetate is lost as an anion. What should be the charge of the mercury? Neutral. And there's lone pairs there, yes. The fate of the mercury is to become elemental mercury. We should see that for a mechanism. Keep track of everything. A neutral mercury atom. That would be an elemental mercury. Toxic. Okay, this reaction produces toxic mercury metal. For that reason, this reaction is not used as much as it used to be. Okay, less favorable to be used, especially on huge industrial scale. Still remains a very classical textbook reaction. Oxymercuration. Why is the second step is called reduction? Okay, reduction. That makes sense because whenever you add H's to something like this, that's a classical definition of a reduction. If you remove H's from something, that's classical definition of what? Oxidation. Okay?
Would the sodium go back and bond with the acetate or no?
Depends on what you mean by bind.
Or make an ionic bond with?
Depends on what you mean by an ionic bond.
I don't think there's any such thing as an ionic bond, but you guys are taught that in Gen Chem. What do you mean by an ionic bond?
Like because the sodium's positive and the acetate's negative, would they come together?
Depends on what solvent is there. Because if it's a lot of water, they'll stay dissolved. If they're dissolved, they're disassociated. So if they're disassociated, I reckon you would say there is no ionic bond.
I mean, we could show a balanced equation on the board, and you could show sodium acetate being formed, but you gotta know the practicalities of it. If it's in solution, it ain't gonna be a solid, it's just gonna be all these ions floating around. And really, the only reason you would show sodium acetate on the board is just to keep track of things. Because ultimately, everything has to balance in terms of charge and stuff. I would personally never call it an ionic bond. I'd maybe call it an ionic attraction or just ions. And use terminology, will sodium acetate precipitate? Not if there's a lot of water, it's one side. So it will always be disassociated. Okay. Oxymercuration followed by reduction. So we're able to make such a product with no rearrangement. It's basically an alternative way to hydrate an alkene, just like aqueous acid, but this way, no rearrangements. Okay? And so that's why the water ended up here, where the original cation was. Or would have been if it wanted to actually form. Okay, next reaction is another way to hydrate an alkene, but this one, interestingly, gives reverse regiochemistry. Same up here. Instead of the water being bonded here, which is where cation might be formed if it was, the water ends up bonded on the outside, the other carbon. That's reverse of what we would expect. That unusual outcome is called a non-Markovnikov product. Up top, that was a Markovnikov hydration. Standard hydration. Where you would expect cation, that's where the nucleophile adds. Here, the nucleophile did not add where we expected cation. We expect cation here. Somehow it added there. That's called anti-Markovnikov or non-Markovnikov. All right? Those terms should be in your textbook. How do we do this reaction? Here we react first with BH3, a boron reagent. Sometimes you'll see B is shown as B2H6. That's just the dimer of BH3. If you ever see B2H6, mark it out and make it BH3. It's just a dimer. All right. This is next week, right? First got to react with BH3. All right, what do you know about BH3? We had it drawn over there.
It's neutral.
It's neutral. Does it have an octet? Boron have an octet?
No.
No octet. It's only got 6 electrons around it. That means it's got an empty orbital. That means it's electrophilic. It would like electrons. Because the boron would like to achieve noble neon configuration. Or would it? Because, like we said, you can never make boron happy. It's got an empty orbital. That's why it's electrophilic. There's no positive charge. These electrons attack boron. Where are we going to leave cation, top or bottom? Bottom, right? These electrons attack boron. Right? What's on the boron? 3 H's. And what's here now? Put a cation in there. What's the charge of the boron over there?
Minus.
Charge of the boron?
Because it has an extra bond.
Well, how many does it own?
3. It owns 3 and has
No, it owns 4. It's
four.
supposed to.
It's supposed to have 3.
Right, so the charge is. Okay. Do you think this is actually formed? Why not?
It'll backbone.
Because we're under B in the handout?
Yeah,
Okay, but other than that, why not?
it's gonna have to back.
What's going to backbond? I don't see a lone pair over there.
The
That
boron.
negative charge over
No, charges don't do anything. Electrons.
here.
What can backbond? There's no lone pair over there. We've only backbonded with lone pairs thus far. Here, instead of a lone pair, would this boron like to get rid of one of these H's? What do we do of boron hydride?
Kicked it off.
It doesn't like being minus. It's like H, you and your electrons go. These electrons break free and move here. Have we ever done such like that?
Yeah.
That's a hydride shift. The difference is, it's not going from here to here, it's going from here to here. A 1,3 hydride shift. Because the boron is 1, where does the H end up? Not on 2, but on 3. Our previous hydride shifts were 1,2 hydride shifts. They went from one carbon to the next carbon. One atom to the next. This is one atom to the third. See, at this point, this is a lot like this. A boron with H's, and this got rid of the H and the 2 electrons. Same thing. It's almost like it is a hydride shift. The hydride gets shifted here. What does that do? Boom, 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 boom. BH2. I'll just show that condensed. How many H's here now? 2. No charge. Nothing there is charged. Do you think this is actually formed or no?
No.
It is NAF. Why?
Backbonding happens at the same time.
It's analogous to backbonding. I'd probably not call this backbonding. It's almost backbonding. I'd probably call it a hydride shift. As soon as I attack the boron is throwing this hydride over here. Okay? As soon as these electrons are attacking here, this bond is being thrown this way, same exact time. NAF. Now your book will probably show a nice transition state here. For some reason, books always like to show a transition state right here for this reaction, especially. Not exactly sure why. Well, I do kind of know why, but I just don't teach it like that. I teach it like I'm teaching it. All right? So, is there any intermediate in going from here to here? No intermediate. Bam. It's one transition state. There you go. What do we do to the alkene? There's a new H here and there's a boron here. Hydroboration. That's what we just did. We hydroborated the alkene. An alkene will react with BH3, and BH3 will add across the double bond, it's called. There's 2 H's, the other H is here. This is in step 1. What do we need to do to get the final product? Latia, what do we need to do to get the final product? We need to remove it. We need to replace it with what? Well, formally, we just need to replace it with OH. We need to replace this with an OH, right?
Under my hand's BH2, what do we need under my hand?
Oh, wait.
Now it's an OH, that's what we need to do. Okay? This second step does that. All right? You got it right here, you can write the second step or whatever. Hydrogen peroxide in basic conditions. Sodium hydroxide, potassium hydroxide, your choice of hydroxide. Okay? We're not going to look at mechanism for this. It's a bit convoluted. I'm just going to call it magic. Okay? Magic step. Hydrogen peroxide replaces the boron with OH, and we're done. Do you want mechanism? I know you want mechanism, right?
Yeah.
You can look it up on your own. I'm just going to call it magic. Hydroboration followed by a magic step replaces the boron. Because there's no oxygen here yet. Ultimately, what did we do? Formerly, we added water to the alkene, because the formula of that, you add H2O to it, now you have the formula of this. Did we react with just water? No, we did a lot more than reacting with just water. But the formal outcome is a hydration reaction. Does the OH end up where the cation would be? If it formed cation? No, it ends up on the other carbon. That's odd. That's called the anti- or non-Markovnikov alcohol product. Oxymercuration gave the standard product. That is, the oxygen ends up where the cation would have been if it had been formed. Russian chemist named Markovnikov sort of recognized this 100 years ago. Standard products versus weird products. Hydroboration gives the weird product. But maybe you wanted to make the weird product. All right. This is very important right here before we erase it. My terminology is going to be the boron throws the H over here, or delivers it. Okay? We'll refer back to this one, stereochemistry, right here. Because the H here comes from the boron, right? Okay, show product. Just do it first with no stereochemistry. On the top. It is just regiochemistry. Just get everything bonded into the right regions. Don't worry about projection, static revolt.
So anytime it reacts with BH3, it's going to create that anti-Markovnikov.
Okay, yeah, a little memorization, note card. Alkene reacts with BH3 and then a magic step. What type of product do you get? What type of product do you get? Well, what's the first word you could say? What type of product do you get?
An alcohol product.
You're an alcohol. It's a way to make alcohols from alkenes. Yes. Okay, what do you know about the alcohol product? What type of alcohol do you get?
Not what you would expect.
Non-Markovnikov or anti-Markovnikov, either way you want to say it. What does that mean to you? The OH is going to be
Not where you, yeah.
not where the cation would be. By the way, here's what books are going to tell you. They're going to tell you to memorize this. Please don't do it. They're going to say that the nucleophile will be on the less substituted carbon. You see how it is? Which is more substituted, that carbon or this one?
The the second one.
That's primary, this is secondary. Yes, the nucleophiles on the left substitute in carbon. And they'll harp on it. Memorize this. I haven't said that once. I told you where the cation would be because that's going to be more universally useful to you. It's going to be not where the cation would be. They'll also say the H is going to be on the more substituted carbon. Did you recognize that it would be there? Didn't matter if you did or not, because I don't think that is as important. I would base it all around where carbocation would be. The books will tell you that the nucleophile is going to be on the least, the H is there, and they'll say memorize this, and don't fall into those traps. I think it's a trap. So, note card. I'm going to get an alcohol here. And it's going to be anti-Mercovnikov. So, is the OH going to be on top or bottom? Well, where would cation be, top or bottom? Cation on top or bottom?
Bottom.
No, cation would be on top, right? Tertiary?
Yeah.
Okay. So where's the OH going to end up in this product? On the bottom. Because we know it's an anti-Mercovnikov reaction. So just show the product. OH on the bottom, yes. What's going to be on the top carbon? Methyl, but what else is there? What's new there?
The hydrogen.
The hydrogen, yes. And overall, what are we adding to this alkene?
Alcohol.
What have we added to the alkene? Now we added water. An OH on the bottom and an H on the top. That adds up to H2O. Again, we did not react with just water. We reacted with a boron. Okay, there's your 6-membered ring with a methyl and OH. Methyl and OH. Here's some stereochemistry now. Will the methyl and OH be cis or trans? Now let's go back and consider stereochemistry stuff. Cis or trans? It all comes from the mechanism. And remembering where did that new H come from? It came from the what? Before I erased it? It came from the, comes from the boron, right? Think about it. Let's take a 1 or 2 minute break real quick. Cis or trans? All right? Go to Vegas, you bet on black or red. All right? Are you betting on cis or trans here? Cis or trans? I think what?
This one might be good. That's it.
You've already got the other product?
This will be standard.
Very good. Very good.
No, your explanation is not right. Need to draw it out, show it. Anybody got sister trans?
Maybe six.
Cis? Why do you say cis?
Well, because in this one, you know, the boron's gonna have to come in from either direction, and whatever direction it's in, the H is gonna go to the other place from that same direction, right? Because it's coming off of the boron, it's not just floating around.
The H comes from the boron, yes. The H comes from the boron. Let's look at this. BH3. These electrons back here. This is now bonded to the boron, but this is now tetrahedral. We can draw this new bond forward or back. It'll be either way. All right? I'm going to draw it forward. Let me draw one of these H's. That's this one. That's tetrahedral. There's an H there going back. Up here is trigonal planar. Carbocations are trigonal planar. sp2. Thus, there's no projection up here. We're going to draw it correctly. All right? Where does the H come from? The boron. This then comes here, and we get what? Forward is BH2. This up here now has a methyl and an H. It's now tetrahedral. Is the H forward or back? Forward or back, Chiral? It's forward. Why?
Because it's coming from the boron.
Because it comes from the boron. Here's the cation, here's the boron. It's coming forward. All right? If it throws an H, the H is boom. It's also forward. Unless it's throwing a boomerang, and then it's going to throw a boomerang. All right? What's going back here on this carbon? The methyl. See, it's trigonal planar, but when this H comes in, it pushes the methyl back to go tetrahedral. Here you go. This is in step one. Now, I didn't say this in our mechanism, But when you do the magic step, when you replace the boron with the what? With the OH, no change in stereochemistry. That is, we just magically replace the boron with OH. No change in stereochemistry. That's some mechanistic, magic mechanism, isn't it? I'd like to know more about that one. Maybe in next class. There's your product. Huh. We don't typically draw in H's, right? So what if we get rid of that H? There's your product. You know the H is there, right? Is your product cis or trans?
Trans.
It's trans. There it is. It should be trans. Because when we refer to cis-trans, we're not referring to H's. We're referring to non-H substituents. The non-H substituents are trans. By the way, stereochemistry is coming fast. We will also get this product. Okay? We're going to say this, plus enantiomer. This is the enantiomer. The enantiomer is where, it's a mirror image. It's different. One way that we're going to say though, the enantiomer is where all your projections are switched. All of them. Dash went to bold, bold went to dash. You also get this here. We'll talk more about it. But guess what? Is it cis or trans?
Trans.
Yes. The enantiomer of trans is trans. Only trans. This reaction does not give cis. That reaction you get no cis product. That's some type of stereoselectivity. Okay, how about the bottom reaction? Bottom reaction? Anybody got it? Yep. Anti-Makarnikov product? Makarnikov product. Cis or trans? That question is not relevant here. You can't have, no. It's also not chiral. This product has absolutely no stereochemistry. We'll see that hopefully going forward. There's no stereochemistry there to consider. Okay. On the flip side, there's some miscellaneous handouts. There's an actual procedure here for an oxymercuration. If you want to read about how procedures are actually done, you can find such procedures on orgsyn.com or orgsyn.org. Stands for organic synthesis. You go there and you look up any reaction you want and you can find an actual procedure. This is now free. For 75 years you used to have to pay for annual subscription to this, but then they've made it free. It's a great resource if you're interested. Drug synthesis here. You're going from 7 to 8. What are they doing here? The intro to this is on the previous page. What are they doing? First off, 9-BBN is a variation of BH3. Occasionally, books will mention that. Okay. For us, let's just call it BH3. Followed by, what's that look like? Magic step? This looks like a hydroboration. By the way, we didn't call the magic step something, but what's it called? What was it called on the handout? Hydroboration? Oxidation. Hydrogen peroxide is an oxidant. And really what's getting oxidized is the boron in that magic step. Hopefully you see that they're reacting this alkene right here. They've now made an alcohol. Let's look at this. If you were doing this reaction, would you make cation on top or bottom? Bottom, correct? So which carbon do you think the OH is going to end up on?
The top.
Antimacromicol. Is that where it ended up at? Yes. Now this carbon is chiral. We'll learn about that going forward, and so we have two different possibilities. There's nothing we can talk about right now. That's an example of a hydroboration oxidation. Then they keep going. The next step is test 3, SN2. They put an alkyl group on the oxygen and they keep on going. You can look at the other things there. Pink sheet, what's next? C. There's only one other reaction we're going to look at, so it's not really plural. Hydrogenation of alkenes. Hydrogen. We're just going to add hydrogen. And whenever you add hydrogen, that's known as what? Reduction. So we can also call it a reduction of the alkene. This is shown on the white handout here. Here's our alkene. Here's our product. What have we added? So we haven't added anything, right? What have we added? We added an H to each carbon. I mean, if you react this with Br2, you would get what? Bromine here and bromine here. And we know stereochemistry if we had it. Okay. Well, what if you add H to? H here and H here. They're just not drawn in because they're H's. Right? Alkene converted to a dibromide. What was the alkene converted to here? Alkane. Reduction to an alkane. It's one of the simplest reactions in organic chemistry in terms of the outcome. You can do this with just hydrogen, which is a gas. You need a catalyst, a precious metal catalyst, such as palladium, platinum, nickel, rhodium. A lot of the transition metals, precious ones. Expensive ones, as opposed to base metals like iron or cobalt or zinc. Only one of these. A student one time thought you had to have all of these. No, your choice. Only one of these. These are examples. Mechanism for this. we're not going to look at a true arrow moving mechanism. Really, because there may not be one. What is the mechanism? These balls are meant to be the metal surface of the metal catalyst. The hydrogen is attracted to that metal surface. There's some physical phenomenon for that, but you often hear about metals absorbing hydrogen. There's some attraction there. I can't say much more. But that attraction actually, okay, there's a lot of vagueness here. It almost like it here, they're showing it breaking those HH bonds. And here's what I say. The pi face of the alkene comes close to that metal surface, and the H's there are shot into the alkene like two darts. Okay? It sounds very scientific, right? Yes. All right. And we add two H's, one H to each carbon. And now both carbons are tetrahedral. There's no intermediate in this mechanism. It's just a transition state. It's also not an ionic mechanism. What's an ionic mechanism?
One that involves
Ions.
Ions. I think every mechanism we've done has had an ion somewhere. You see any ions in this mechanism? No. It's not an ionic mechanism. So this is just simple terminology or something, just a simple recognition of that. Importantly though, both H's come from the metal, so when we start talking about stereochemistry, the positioning of the H's, are they going to be same side or opposite? Here we go. Same side or opposite?
Same.
You're the metal and you have the H's. Here are two H's. Here's the alkene walking down the road. You shoot them in, alkene. Two hands. Now they're bonded. They came from the metal. Are they on the same side or opposite? On the same side. They came from the metal. Unless you threw one of them a curveball and it came back here. No. The H's are said to add how? I underlined it for you. It's a syn addition. And syn is means same. It's synonymous with cis. Syn and cis. Syn is more of a verb whenever it's syn, where cis is more of the outcome. Syn addition leads to the H's being cis. Okay? So that's important stereochemistry. What else can we show here? We could get the same product if we hydrogenated this alkene. Everybody agree? We had a 2H here, it'd be the same product. Recognize that? Your choice of catalyst. Question. Which route to pentane would be more exothermic?
The second.
These reactions are exothermic. Why? Because we're going from a pi bond to what? Two new sigmas. You can do your calculations, but I guarantee you it's going to be exothermic. Which one would be more exothermic? How would you figure this out? Reaction coordinate diagram. Right? Boom, boom. I'll do it simplistically. A, B, C. They're both going to C, right? Here's C. A and B should be higher than C, right? Which one is A and B? Which one of these is A? How do you compare A and B? They're alkenes. We did this last week at about 10:40 one
Does it
day.
have to do with the constituents?
Which one's more stable?
B.
Which one's more stable? B. A is higher in energy. They both go to C with a transition state. Which one gives off the most heat? Which reaction gives off the most heat? Reacting A. Why?
Less constituents.
Because A sits higher, it has more energy to give off when it comes to C, right? A to C gives off more heat. It all comes from your reaction coordinate diagrams. They're very useful to help organize your thoughts, right? Right? You can label your axes. Over here. If we hydrogenate this alkene with palladium, by the way, sometimes these metals are dispersed onto charcoal, carbon. It helps give the metal more surface area. So palladium on carbon, or nickel on carbon, or something. Platinum on carbon. If you do this hydrogenation, you're going to get this product. Will these two groups be cis or trans?
Cis.
Well, I've already given you the answer. They'll be cis. Why?
Because the hydrogens are coming from the same side.
Because the H's are cis. The H's are on the same side. Thus, these two alkyl groups must be on the same side. This is where both H's came in from the back. They could also come in from the front. And that would give what? We have the enantiomer, and that's the enantiomer. But the enantiomer is also cis. This is where both H's came in from the front. Okay? Because anytime you react with an alkene, which is planar, you can do it from either side. That reaction will not give trans. Because we know how the H is coming. Okay, that's hydrogenation. By the way, this is called heat of hydrogenation. Let's finish this up over here. Very similar question to what we did here, except there's 3 alkenes. Okay. Question. Which one of these alkenes will have the highest heat of hydrogenation? Now, heat of hydrogenation is not a delta H. It's the opposite of delta H. The delta H would be negative, right? But when you call it heat of hydrogenation, you leave it as a positive term. It's the heat that's giving off. This reaction gives off heat, so that it's giving you something. Right? Which one gives off the most heat? Left or right? What's the difference in these two? That's cis or trans. These are both hydrogenated to butane. Which one gives off the most heat? Why would the trans give off the most heat? It's more stable, thus it sits lower. Which over here gives off more heat, A or B? Why does A give off more heat?
It's less stable.
Because it's less stable. Less stable, it contains more energy, which means it's less stable. Which has higher heat of hydrogenation? Oh, there, right?
Yeah.
While we're here, let's ask a question on the right. Which of these alkenes reacts fastest with HBr?
The first one.
Why the first one?
It has a lower heat of hydration, so it'll happen faster.
It has a lower what?
Heat of hydration, right?
Heat of hydration. Tell me again.
It has a lower heat of hydration. Like if you were to do the, right? If you do the,
What's a heat of hydration?
Hydrogenation.
or hydrogenation, sorry.
Yeah, but we're not hydrogenating, we're reacting with HBr. Which reacts fastest with HBr?
The one with more oxygen.
One of these reacts 100,000 times faster than the other with HBr. This is a little bit apples to oranges. How can we answer this though? What could be an argument we can look for? Anybody see anything that you could give a rationale for why it would react 100,000 times faster? Carbocation formation, that's often something we look at. Which one would? What would be the rate determining step in reaction with HBr? What's the rate determining step of a reaction with HBr? To form what? Formation of the carbocation. Which one's going to form a carbocation faster? One on the right. Why? Because it's going to form a tertiary carbon. One on the left will be a secondary carbon. If we were to do this with a reaction coordinate diagram, it's not as straightforward as these because you've got two different starting points and two different here. 2 and 2, and so it's not as simple as 2 to 1 or 1 to 2. They're not starting at the same place, nor are they going to the same place. But basically, looking for the best cation, tertiary. Tertiary cations are easier to form, everybody agree? That gives you the answer here. That one reacts 100,000 times faster.
Could you do acid versus base for that one?
You would?
Could you do acid versus base for that one? Could you look for the most basic?
I mean, those are not going to be basic. Basic in what sense?
Well, I mean, like look for stability and say that the right one looks less stable, and so it would react faster with an acid.
I'm not quite following you. Write it out and show it to me again, and let's see what you're talking about. Down here. This one's a little more straightforward because, as we'll see, they're either starting or going to the same place. Both of these give the same product. Which reacts faster? Top or bottom, which would react faster? Hopefully you do see that they would give the same product. Which would react fastest?
That could be a reasonable argument, but I would ask you to sort of clarify that some. We do a reaction coordinate diagram and call this A, B, C. Let's just do the rate determining step. Talking about rate, let's look at the rate determining step. They both form the same cation. Let's call it C. And let's put C here. They both form that upon reacting with H+. Where do you want to put A and B? Lower. But they're different, right? Which one's A? We talked about this last week at about 10:40. Which one's more stable?
B.
B. Which one is going to form the intermediate fastest? At some point, they become the same. They both go to the same. Which one's going to be easier? A will be easier. It's like when you climb a mountain, right? Here's the top. Who's going to get there easier if this is a starting point? This person will get there faster, right? A will get there faster. Which reaction is faster? A. They both form tertiary cations. Okay? This is some of this type of question. You got to figure out what argument to make. There's a couple of miscellaneous things there, but let's move ahead. You may refer back to those on hydrogenation. So those are your alkene reactions. How are we doing with that puzzle? Gold sheet? We're looking at those? Okay, here's some warm-up questions for stereochemistry. I actually do have some DQ questions for stereochemistry. What is stereochemistry? Projections of the bonds. Okay? Same connectivity, how they're projected. Like the cis and trans example. That's a classical example of stereochemistry. Is stereochemistry important? Well, of course it is. Or we wouldn't be. Let's talk about it. Here's an example. What's the difference between cellulose and starch? Stereochemistry. Cellulose. We've got these
Sugars, which is a 6-membered ring with an oxygen. Okay? Saccharide. Polysaccharide, it's polymer. But between the two rings here, they're bonded via an oxygen. But in cellulose, both of these bonds are equatorial. They're both projected to the carbons of the next ring, just like over here. Bonds are connected to the carbons of each ring. But over here, one bond is axial and one's equatorial. And this is stereochemistry. They're connected at the same spot, but just projected or oriented differently. Makes a huge difference. Our bodies can digest starch, but not cellulose. Stereochemistry makes a big difference. If we could digest cellulose, well, then we could eat trees and we'd have a shortage of food, I reckon. All right? Down at the bottom, there was a drug developed in the late 1950s to give to pregnant women to treat nausea called thalidomide. Have this structure here. The difference is right here. All right? You can't really tell it, but these are stereoisomers. You'll be able to tell it once we talk about chirality. One stereoisomer was a good drug, the other one led to toxicity. When they were developing the drug, they just tested the good one. But when they started manufacturing it, something messed up and went bad. They started manufacturing the bad one. And so they ended up giving pregnant women. Led to toxicity, and it led to babies being born without like limbs, no arms. And those were actually sort of the better cases. There were even worse deformities than that. Now that's showing some kids there that were called thalidomide babies, called back then. Eventually a nurse helped identify what was going on, mainly in the UK, England, some of the United States, but then the nurse was helped figure it out, and President Kennedy gave her some type of medal. Okay, lots of examples of the importance. We have a little diagram here. Isomers. Same formula, different compounds. All right. What type of isomers can you have? You can have constitutional isomers. These have different connectivity. Okay. Thus, different name. Different name. Or you have stereoisomers. Okay? These have same connectivity and same name. Because when we name a compound, we don't worry about the projections when you name it. We will see that. Okay, the blue is our outline. And we'll start with chirality. Chirality comes from, I think, Greek word for hand. Okay? And in the very back of this handout, there's a touch of history where such is mentioned, how some of these terms came about, what scientists or chemists were involved with coming up with this. Chirality, mainly because your hand is a chiral object. Okay? Everybody's got a right and a left hand? Yeah? What's the relationship between these two hands? They're mirror images, right? We've known that since year old. Okay. Are they the same or different? Well, this one can fit into a right-hand glove, but this one can't. Okay. Do they have the same connectivity? I got a thumb next to a pointy finger. Well, I got a thumb next to a pointy finger. Way away from the thumb, I got a pinky. It's the same connectivity, they're just sort of inverted or something, or opposite. They're mirror images. If that looks in the mirror, what does it see?
The other one.
It sees that. Okay? But they're not the same. How do we know they're not the same? Other than the fact you can't put that one in the right-hand glove. One of the common ways if something is the same is you can stack it. Right? Saucers in your kitchen cabinet. You just stack them 6 high. Well, they're all the same. They just stack on each other. Can you just stack hands? No, if I tried to stack it, the thumbs are going to be opposite. We say that they're not superimposable. Stacking is called, can you superimpose them? No, you cannot. That tells you they're different. Okay? So what do we have here? Mirror images that are different because we cannot superimpose them. Are all mirror images different? How about this? If this looks in the mirror, what does it see? Do you agree that if that looked in the mirror, it'd see that looking back at it? Right? It's mirror images. Are these the same or different? You know they're the same. It's 2 identical paper clips, right? Okay? You could superimpose them if it was flatter, but I mean, if you could take that like a, what do you call it, a hologram or something, and you could put it right on top of the other. Okay? Yeah, they're the same. Mirror images are the same. Okay? Mirror images that are different, that's called chiral or chirality. This is okay? The idea of chirality. My hand is chiral. That's where the term chiral came from. It means hand. Is this object here chiral? That is the mirror image different? No, the mirror image is the same. So this is not chiral. How can you more readily look at that object right there and tell that it's going to be chiral or not? What's a tricky way or a fast way to tell if this is going to be chiral? That is, if the mirror image is going to be different. What about this chair here? Whole thing, chiral or not? What about the trash can? The pencil sharpener, chiral or not? What's an easy way to tell? Do you always have to take it and make the mirror image? All right. Here's the way to tell. If something has a plane of symmetry, the mirror image will be the same. Does this have a plane of symmetry? Plane of symmetry. Can you cut right through this object and you have half on one side, half on the other? Yes, you can see right through there I'd have half a clip on one side, half on the other. What about my hand? Does it have a plane of symmetry? No, if I cut right through here, I'll have a thumb on one side, not on the other. What about right through here, though? What if I slice right through there?
No.
Just like half a thumb on one side.
Have what?
Well, half a thumb on one side, half a thumb on the other.
Well, half a thumb can be half a mirror and half a thumb. I mean, you half a finger on one side, half a finger on the other. Is that a plane of symmetry right through there?
Yes.
It's actually not, because I'll have knuckles on one of my cuts, and on the other cut I'll have palm. You see, if I had knuckles on both sides, then this would be a plane of symmetry. But I don't. Right? Look right here. I'll have a nail on one of my sides, and there's no nail on the other. So that's not. And what if this was a slice of bread, old white loaf bread? Then it would be, because you'd have you just have two smaller pieces of bread. Okay? Looking for planes of symmetry. Okay? Does this pencil sharpener have a plane of symmetry?
No.
I think the answer is going to be, well, hold on.
You can slice it down the middle.
Well, what way? This way?
No, like this, like this.
If you were to
No,
put the
that's
handle, if you were to
like
put the
this.
handle vertically,
If
and
you
then
were to-
slice it
yeah.
down vertically.
Yeah.
Like this?
No, put it down, put it, there you can slice it down.
This one?
Forget that it's attached to the wall.
Like this? No, you'd have an attachment in the back, and there'd be no attachment over here. I'm not seeing a plane of symmetry. Thus, I think the mirror image of that would be different. I think the pencil sharpener is Chiral. Okay, looking for a plane of symmetry, I'm going to call that where's Waldo. Okay, we often look for Waldo. If you can find Waldo, that means the object is not chiral. Okay? A lot of that is discussed here. You can read my own view. I'd recommend reading your textbook view too. Let's look at this compound here. By the way, enantiomers. What do we call these guys? Right hand, left hand. In the chemistry world, we call these two enantiomers. Mirror images that are different, the two are called enantiomers. Let's look at the enantiomers of of one bromo, one chloroethane. This. Does it have an enantiomer? Is this compound chiral?
No.
Yes. 'Cause
Or
it doesn't have the-
yeah, it is chiral.
It doesn't have the symmetry.
Does it have a plane of symmetry or not?
No.
How do you know it does not?
Yeah, you worry about it.
Let's make a model of this compound. Well, first off, this compound doesn't have projections drawn correctly because this carbon's tetrahedral. We got to have two in the plane, one forward, one back. All right? Let's draw this like this. Chlorine. Let's put the bromine forward. This is more appropriate, right? And we can also put bromine back. On the board, carbon, chlorine, chlorine green. Let's make the bromine red. Forward. What's going back on that carbon?
Hydrogen.
Yeah. There it is right there. Everybody agree? Okay, now let's look at it. Do we see a plane of symmetry?
No.
Because I can turn it all any way now that we got it. Plane of symmetry? How about right through here? Half a red on one side, half a red on the other. Too bad. Black over here, green over here. No. Well, let's turn it here. You will never have a plane of symmetry. Okay? By the way, what if it's, instead of green, this was another carbon? Do we have a plane of symmetry now? Yeah, you see? If both of those are carbons, boom, right through here. Carbon on one side, carbon on the other, and you're slicing right through the red, half a red on one side. Okay? But we don't have that. why is there no symmetry here? Very classical and most common reason why. We have a tetrahedral carbon with 4 different things attached. If you have that, that is a site of no symmetry, asymmetry. This type of site is called a chiral carbon. Okay? And a chiral carbon we can indicate with just some type of star. Because there's no symmetry at that carbon, it ruins the symmetry for the whole molecule. Oh no, I don't want to do this, sorry. Let's draw the mirror image of that compound. Mirror image. As is, if it looked in the mirror, what would it see over here in the mirror? Would it see this? Now it's a little bigger.
It's the same thing.
Bromine like both place in the wood.
Hmm?
Bromine would be bad.
No. Those are mirroring. If I'm over here with my arm forward, the person over there would have their arm that way as well. The mirror image of this would be this. Correct? If you look in the mirror when you get home and you hold your arm up here, your mirror image is going to have your arm which way? That way is also. So, these are mirroring, right? Is this the same or different? Same or different, guys? No, those are different. Why do you say they're the same?
I know, because if you did flip it, then the bromine would be bad. If you tried to stack them.
No, we've already showed how to answer this. The first compound, does it have a plane of symmetry? No. No, didn't we walk around and say no? What does that tell you about the mirror image?
It's not the same.
Not identical.
The what?
They're not identical.
They're not the same, right? We've already answered that. Those are different. How do we know? Because it doesn't have a plane of symmetry. Those are different. Where'd the model go? Where's it? It's on the
Did you drop
floor.
it?
On the other side.
That was that one. And this one is that one.
Mhm.
Aren't those mirroring each other? This looks in the mirror, want to see this?
Yes.
Yep.
Mhm.
Okay, same or different?
Different.
Different.
We're going to answer that. They're different because, look, there's no plane of symmetry. That tells me the mirror image is going to be different. Okay? Are they indeed different? Well, let's try to superimpose them. Here we go. Black on black. Uh-oh, those won't line up. Well, we can make the greens line up. Well, now these don't line up. You will never be able to line them up. They're not superimposable. Mirror images that are different. The two compounds drawn there are called enantiomers of each other. Okay? Now the same connectivity, they're both this compound. One bromo, one chloro, ethane. These are enantiomers. largely because the presence of a chiral carbon ruins the symmetry, making the mirror image different. Okay? How can we distinguish between these two? What type of terminology? We use R and S. With our hands, we use right and left. Here we're going to use R and S. We do this a lot like the E and Z nomenclature. We label priorities. Okay? Priorities on the first carbon. Bromine 1, chlorine 2, methyl 3, H in the back. Okay? With a low priority group in the back, we then do priorities. Is it clockwise or counterclockwise? 1, 2, 3, priorities clockwise. Clockwise is R. This is said to have the R configuration. Over here, priorities, bromine 1, chlorine 2, carbon 3. What's 4? It's in the back. With the low priority group in the back, what's the configuration at this chiral carbon?
S.
Counterclockwise is S. So the name of this compound would be S. And then the name. Where this one would be R. And then the name. These two are enantiomers. More broadly, these two are stereoisomers. Different same connectivity, different projections. Last comment. We can only distinguish between stereoisomers with some type of stereochemical descriptor in the front of the name. Well, stereoisomers have the same name. We just use a stereochemical descriptor. We will see other stereochemical descriptors. You already have seen some, like E and Z terminology for alkenes. That's a stereochemical descriptor. Okay? See some of you in the lab this afternoon. We'll meet down here. Have a good day, guys.
It was my first time after the same Wednesday, so I was overwhelmed. Yes. And then like in the score bowl, it gets sizzling loud, but it's like such a cool experience.
Did you guys do the walk? So when we were at stadium, very close to Texas, the kids actually went to walk down the street. Everybody was very warm the stadium.
Yeah, walk.
Did it change?
No.
Like when you take the ages.
Oh.
The conscious.
It's like an hour into the game started.
Oh, yeah, we came like on the go.
That was important because it's like everyone's there and it's so much fun. Everyone's dressed up, everyone's like going out. So I was like,
Oh, fun fact, remember at the beginning someone got like a red card?
I don't want to forget. I watched like the last like 10 minutes. So that was out. Like, so like, who got it?
He had some kind of penalty. I don't remember if it was like.
First side?
Huh?
Was it Archie or
No, it was the Philadelphia team. It wasn't Atlanta United. But I was actually